Alright, let's take a look and see what we have for problem 7. A closed tank, 1 meter cubed in volume, is filled with water at 1 bar, 80 degrees C. A second identical tank contains 20 kilograms of steam at 20 bar. What is the mass of water in tank 1? What is the temperature and phase in tank 2? And then the contents are mixed. So before we mix, let's get down part A and B and fully categorize our systems. Okay, so let's just take this as tank 1. Okay, so when I look at tank 1, so our total volume is 1 meter cubed. Our pressure, and so let me label this V1, P1 is 1 bar, and T1 is 20 degrees C, or 80 degrees C. So first and foremost, I have two independent variables are specified. Two intensive independent variables are specified. So if I had a single component, single phase system, I know that the state of my system is fixed. Okay. But first, let's figure out what we have, and I'm going to need to get the specific volume from this so that I can use that to calculate mass given the total volume. Alright, so I'm going to go over to my steam tables, and we could start by looking in superheated, since that's where we are from the last problem. So at 1 bar, my saturation temperature is 99.61. So since my temperature is less than my saturation temperature at that pressure, that's going to tell me that I have a liquid. Okay. So since T1 is less than, I'm going to say Tsat at P1, we have a liquid. Okay, so I need the molar volume. Okay, so what I'm going to assume is it's been mentioned in the book a lot that as long as you're removed from the critical point for condensed phases, that most properties are relatively insensitive to pressure. And so what I'm going to take that to be is that my specific volume at T1 and P1, okay, is approximately equal to my specific volume, okay, at saturation, all right, in my liquid phase at the same T1, all right, because I know, that, so if I flip this around, right, so if I go to my saturated steam tables, my temperature is 80 degrees C, okay, so 80 degrees C, second column should be pressure, so 80 degrees C, my saturation pressure is 0.4741, okay, so my actual pressure is 1 bar. So what I'm assuming is that my molar volume of my liquid at 80 degrees C and 1 bar is approximately equal to that at 80 degrees C and that 0.47 bars, right? The corresponding pressure at saturation. Okay, I'm assuming that difference of a half bar can be taken to be negligible. So from my saturated steam tables, okay, at 80 degrees C, here's my saturation pressure. Then here's the specific volume of my liquid, is this first one, is 0.001029. 001029. This could be meters cubed per kilogram. Okay. So then what is the mass? Sorry. So in part A, okay, what is the mass? Okay, well, I know that V1 is equal to V total, okay, divided by mass. So therefore, M1, my mass in this initial tank, is going to be equal to V1 total divided by V1. Okay, and that'll be equal to, let me type it in here so I have it, so V1 total is, 1, and that's meter cubed. And then V1 of my liquid is 0.001029, and that's meters cubed per kilogram. So my mass is going to be equal to V1 total divided by V1. Okay, so my mass is 971.8173 kilograms. 971.8173 kilograms. Okay, and again, this is a liquid. Okay, and hopefully it makes sense where we got the specific volume from. Since we're in the compressed liquid phase, we're assuming that the pressure doesn't change much with respect to pressure. So we went to the saturated steam tables so that we could get the liquid value at our specified temperature. Okay, now B. Okay, let's figure out way of in B, or let's call it tank 2. Okay, so we have an identical tank with 20 kilograms of steam at 20 bar. Alright, so what I'm going to take this to be, so by identical tank, I'm going to take that to be that the total volume of the second tank is 1 meter cubed, right? I have the same size container. Now here, we're told that the mass in the tank is 20 kilograms of steam. So we have M2 is 20 kilograms. And our pressure is 20 bar. Okay, so the first thing I'm going to do is I'm going to calculate the specific volume. So I know that V2 total is just V1 total. And mass 2 is 20, okay, and that's in kilograms. So V2 is V2 total divided by M2. So my specific volume is 0.05. So I'm going to have V2, okay, which is equal to V2 total over M2. It's going to be 0.05 meters cubed per kilogram. All right, so now the significance of this is I know two intensive properties. I know specific volume and I know pressure. So that tells me then that the state of my system is fixed. So let's see what we have. So what I'm going to do is I'm going to go to my superheated steam table since it's organized by pressure. And I'm going to find a pressure of 20 bars. Okay, here we go. So at 20 bars, okay, here's the specific volume of my liquid phase and vapor phase at coexistence. So our specific volume of 0.05 is between that of my saturated liquid and my saturated vapor. So what this tells me then is at 20 bars, we have a two-phase system. Why? Because V2 liquid is less than V2, which is less than V2 of my vapor, right, at saturation. And so What do they want to know? What is the temperature in tank 2? Okay, so that tells me then that the temperature in tank 2 is equal to the saturation temperature at that P, and that's going to be 212.38. All right, so I've got A and I've got B. All right, so hopefully that makes sense. So our volume is between the two specific volumes at saturation at that P, so that puts us in a two-phase region. All right, so now the contents of the two tanks are mixed together in a third closed tank whose volume is 2 meters cubed. Heat is added or removed as needed to bring the final temperature to 175 degrees C. What is the final pressure? Alright, so the contents of the two tanks are mixed together in a third closed tank whose volume is 2 meters cubed. So it's equal to the sum of the volume of the two first tanks. Heat is added or removed as needed to bring the final temperature to 175 degrees C. What is the final pressure? Well, let's do it. All right, and actually, this one I think it's tempting to overthink it, because so what I'm thinking is, all right, so if I'm mixing tank A and B, okay, so, and all we want to know is what's the final temperature. So tank A contains 971.8173 kilograms of water. Tank 2 contains 20 kilograms of water. I'm going to take that mass and I'm going to put those in a new tank with a volume of 2 meters cubed. Okay. So I should be able to calculate the specific volume of that tank. And I know that the temperature of that tank is going to be 175 degrees C. So that should give me two intensive properties which I can use to fix the state of my system, which I could then use to find P. Okay. So let's give that a try and see if it works, right? There shouldn't be a need for any sort of energy balances, right? Because we're not asked for the amount of heat. So let's see what we have. So if I look at tank 3, so let me just call this tank 3. Okay, so tank 3, right, is 2 meters cubed. Okay, the temperature, right, in kind of tank 3, this final state, is 175 degrees C. Okay, and since I'm mixing the contents of tank 1 and tank 2, all right, the mass in tank 3 will be the sum of M1 plus M2. Okay, so let's see what happens. Okay, so if I do that, so then specific volume in V3 would be V3 total divided by M1 plus M2, and that'll be equal to, okay, so let's do this. So part C, so V3 total is equal to 3. It just so happens it's equal to V1 total plus V2 total. And so V3 is going to be equal to V3 total divided by M1 plus M2. Okay, so V3 is 0.003. 0.003, and that's meters cubed per kilogram. Alright, so now let's take a look at our steam tables and see see where we are. So I'm going to start by going back to my saturated steam tables and hoping 175 is on there. Right? It's not exactly, but that's okay. So 0.003. So if I'm looking at 174 and 176, okay. So at 174 and 176, okay, here's VL, okay, and here's VV. All right, so VL's 0.001, just take it to be, and VV is 0.2. Okay, so we're 0.003, which is greater than 0.001. All right, so we must have a two-phase system. All right, so we're going to be at two-phase coexistence. All right, cool. All right, why? Because I'll say V3 liquid is less than V3 is less than V3 vapor at 175 degrees C. Okay, so we have a two-phase system. And what are they asking? What is the final pressure? Okay, so we're going to have a two-phase system. We know we're between 174 and 176 because our temperature is 175. So all that means is we're going to have to interpolate then to find P, since we're saturated, right, and we have a two-phase mixture. Okay, so let me add new page after. All right, and it looks like we're going to have more liquid than vapor since we're closer to that liquid density, but we'd still fall between the liquid and vapor, which puts us in two-phase. All right, so that vapor would expand to fill my tank. So let's write down what we have. So temperature in degrees C, pressure in bar. All right, we're going to need to interpolate. So we had 174s in the table. We need 175, and we have 176. So 8.716 is my saturation pressure at 174. And at 176, it's 9.137. So if I'm going to interpolate, okay, let me create. So, my temperature, again, is 175. I create my vector of temperatures. I have data at 174 and 176. Okay, the corresponding pressures were 8.716 and 9.137. So to estimate P, so P is going to be interp 1, so linear interpolation. So my x variable, my independent variable, would be T, and estimate the value of P at that T. Okay, so I get a pressure of 8.9265. So P is equal to 8.9265 bar. Okay, and this one, the problem did honestly seem a little odd because there shouldn't be a first law balance or anything of that nature involved. It's just I'm taking the mass of tank 1, mass of tank 2, combining those in the third tank. So since I know the total volume and I know the mass, I could calculate the specific volume of that tank, and I know the temperature. So that gives me two independent intensive properties, which pins down the state of my system. And since my specific volume is between the saturated liquid and vapor at 175 degrees C, it must have a two-phase system. Okay, so no first law balance here, but fun playing around with the steam tables and figuring out what we had. Hope that helps.